Hello everyone, welcome to Fine Element Method tutorial. Today we are going to use Abaqus to apply dynamic analysis. We are going to use two different approaches. One is in time domain, the other is in frequency domain, and compare what's the difference between these two approaches. Let's see the problem statement. So we have a plate which is pinned on one edge and also jointed by two aluminum beam. The aluminum beam has a circular cross-section of 0.25 inches square. And the rectangular plate is 30 by 80 by 0.7 inches, so it can be considered as a shell. The plate is made of steel while the beam is made of aluminum. There's a load which is 100 pounds, a kilopalms block with 10 by 10 inches contact area. Initially, it was put on top of the beam plate, and then it was suddenly removed, and this remove of the weight is simulated by 0.2 seconds of linear decreasing load. And we are going to apply the directly time integration and frequency domain analysis to this one. So for time domain analysis, we are going to apply the general static step to represent the loaded initial condition. And then we're going to do the dynamic implicit, which is basically is considering each time iteration, like what does it related to the previous step. So it's directly doing analysis on the time for different time. On the other hand, we have frequency domain analysis, which we have first apply the modal analysis to obtain the resonant frequency and the mode shape. And then we have the static analysis to which we use linear perturbation static to apply the preload. And then finally use this initial condition, go to modal dynamic analysis. And this is basically considering your model, motion is a linear combination of all the mode shape of your resonant frequency. So this is basically converting your time vector to a frequency domain and solve this problem response in frequency domain. And we'll show like how to apply this one later in Abaqus. So let's go to Abaqus setting. First, we create our model plate, 3D shell plate, planary plate. Use the rectangular tools to do 0, -15, 0, 80, 15. So you have a 30 by 80 by 30 inches square here. Now create a beam. Sorry. So beam element, 1 planary, and the dimension for that, this is 20 and this is 40. So we're going to do 0, 20 to 40, 0. Now we can create a property. Aluminum density is 0.1, while elasticity 10E6 and 0.3. Create steel density 0.28 and create elasticity for that 10E6 and 0.3. Now create a section. Create aluminum section. Aluminum is the beam, so we do beam, and cross-section, which is a circular cross-section. with the radius is 0.282. Poisson's ratio 0.3. Material aluminum. Create another section steel, which is a shell element. Thickness 0.7. Material steel. Now assign section. We don't need to create set. Aluminum for the beam and steel for the plate. And for the beam element, you need to assign the direction. So since our cross-section area is circular, it doesn't really matter like what is a N1 direction or N2 direction, just leave it default. You can see the N1 direction is pointing that one, N2 is the other one, and tangential direction is along the beam. If your cross-section area is not circular, you need to pay attention to where is your N1 direction and where is your N2 direction. Now in assembling, create plate independent, create beam independent. Notice that originally your beam is on XY plane, but we want it to be on XZ plane, so you need to rotate about X-axis. Use the rotational tool, select this beam, and select X-axis, which should be initially 0, 0. Here is 1, 0, and rotate 90 degrees. You should in XZ direction now. Don't forget to click OK. Now do translate. Translate this one from this point to this point. Since we need another one, we use linear patterning. And originally this calculated to be 0, but it doesn't matter. So choose the direction, which is this direction. Well, it cannot be 0, so we enter a random number for that, but change it back to 1. And this one, 30. Notice that you need to select the direction of this length. Now you can see that you have 2 lines here. When the model is done, we need to create a partition for the loaded area. The loaded area, we want it to be a little bit close to the end so that we can have torsional motion to that. So create a partition to this plate. Use a rectangular tools from the most right up corner and use the dimension tools to control the contact area. Both horizontally and vertically should be 10. And to make the mesh better, we can actually cut through this entire instant. So you have a shape like this. This is our loaded area. Now we can go to mesh type, use structure here in the quadratic element, and assign a seed 0.5. You can see that it's fine enough. For this, especially mode shape analysis, it's better to make it as fine as possible. You won't have too much element here. And it's plate and beam elements, so it should be very fast in computation. Now we need to assign some data point for that. First is 40, 0, which give you the center point, and then 40 minus 15, 40 plus 15, which is a 2. This 2 node is going to be coupled with the beam. And now we can create set for that. To create set, before creating set, first we select this, select the instant, select this 2 instance, and then hide it. Now in your set manager, select the node, left plate. create another one, right plate. To represent the coupled point on the plate. We also need 3 points to output the result later. So let's call it reference 1, which is this point. Reference 2, which is this point. And reference 3, which is the center point. Now use these tools to leave only the beam. Create set left beam, which is the coupled point on the beam. Right beam. When everything is done, go back to your interaction first. So show them all, and now create a type. Left tie. So we are going to tie the node on the plate with the node on the beam. So select the node of the plate, left plate first. Select the node of the left beam. And we don't couple the degrees of freedom, rotational degrees of freedom, but we can make a little bit adjustment, although they're already kind of overlap with each other. So create another one, right tie. So you should have the right plate coupled with your right beam. Again, no rotational coupling. See this, there's 2 circles here represent that it's already coupled. Now we can go back to the step. For the time domain, we're going to create static first and then dynamic implicit. So for static, we call it load, loading, static general, and just leave it default. Create another thing, call it unloading time, and use dynamic implicit. Now our time of simulation, let's do 10 seconds here. So leave it 100 frames, but then the increment, we use fixed increment. So 10 seconds separating into 100 frames, so each frame should take 0.1 seconds. Actually, let's make it longer, 20 seconds. So increment, we can be 0.2 seconds. And rename this one as loading T, which means time domain. Now we need to modify your history output here. So for your history output, every 1 increment, we don't need that much output. What we only need is the U and the mixer stress. So now create another reference 1 time. In the unloading T. Sorry, this is field output. Field output is there. We don't need to make any other changes. Now we create a history output. Originally, your history output, we can rename it as reference 1. So for reference 1, we don't need that much. We only need displacement. So it should be set, and then choose the reference point, which is this corner. We just select every 1 increment, and what we only need is the displacement. We only need actually third. which is Z component of your displacement. Create ref2. Same thing here, set every one increment ref2 and only U3. Ref3, set ref3 and then 1 displacement only U3. You can even move it to the right, so we don't need any history output from the loading. We only need unloading. Now in your load, first create boundary condition. All boundary conditions should be the initial step. Let's call it ping. Ping is displacement rotation. So as the problem statement says, this edge and this 2 point, hold shift and select this 2 point, should be ping. So ping is constraint on all displacements. Now we can apply load. First, we create a load, which is pressure, and apply on this one, run total force, and then it should be 1,000 pumps pointing downward. Now create the unload region. Before creating the unload, see that this load is going to propagate to the next step, but we don't actually want it. So what we do is we deactivate that. So we can create the unload here. It should be in your unloading time. Again, pressure, and again this one, which is 1,000 total force, but now your amplitude should be different. Create a decreasing amplitude from tabular. We create another insert row after. The time should be 0, and when 10 is equal to 0, amplitude should be 1, 0.2 should be 0, and all the way to 20, which is our maximum analysis time, is still 0. So if you use the tour amplitude plot to see the decreasing amplitude, it basically looks like this. This is very similar to an impulse loading. From 1 suddenly drop to 0. Now we change the amplitude to decreasing. Don't forget to change your amplitude back to decreasing here. And don't forget to change it to total force, 1,000. So it should be like this. Don't forget to deactivate this force. Now in your job, you can create your job. Call it DTI directly time integration with 100 frames. For directly time integration, we can use parallel computing, which we can use for my computer. I have 12 logical processors, so I'll use 10 of that. Since this is not a large problem, it should be pretty fast. Oh, the property. Oh, I think I didn't click OK. So when you assign the direction, don't forget to click the OK here. So submit. Now request for, I think we have history output. So history output. Oh, we don't need any history output for loading T. We only need the unloading region. So that's fine. So we can directly submit. Click yes. It should be pretty fast. After the input file was created and submitted, you can actually go back to change it. Now I want to compare with a finer time mesh. That means we still keep it 20, but this time we want it to be 500 frames instead of 100 frames. So this should be 5 times smaller than this one. So 0.2 divided by 5 is 0.04. Everything we can leave it the same, but at job we create DTI 500 frames. Temp here. So you can submit now. We can kind of check what's happening here. So you have stress concentration at 2 points. Originally, it started vibrating, but you can also see a little bit torsional loading here. See, it's kind of rotating between these two. And it has a sudden jump. And while this one will take longer time since it's 500 steps, you can see that it's pretty kind of slow. Every time it has only 10 increment. That's because I have 10 processors working there. But on the other hand, if we use frequency analysis, it will be way faster. So to do frequency analysis, we uncheck all the time domain analysis step. Now we create frequency analysis, loading. First is modal analysis. Modal analysis first. So it should be in your linear perturbation frequency. And I'm going to take 30 mode because I think 30 mode will converge. Now, after you have your modal analysis, we can create the loading F. This is still doing time domain analysis, but this is static, so it doesn't really matter it's frequency domain or time domain. So in here, you have a static linear perturbation and just leave everything default to create a preload. And finally, we need a unloading. So unloading, we use dynamic here, modal dynamics. And the time of total is 20, and we directly use the finest mesh, which is 0.04 for time increment. And here, we create the damping model from the first mode to 30 mode. And first, we do the undamped, do the model without damping. Since normally higher mode will have larger damping, but here we just assume all of them doesn't have the same damping coefficient, which is 1%. Now it's 0% because it's without damping. So after that, we can check the history output. You should have 3 of that, and we actually don't need that much. This modal dynamics, we need that for the mode shape. And here, instead of everything, we just need the strain and displacement, stress and displacement. And also from here, we can create our own field. So rename this one as reference 1, and then use the set and reference 1 every one increment, and we don't need that much. We only need the displacement and probably just the stress. Sorry, this should be whole model because this is a field output. It's better to be whole model, but it's still like you need to change it to 1 so that we can capture all the step, and then we can rename it back. And now we can create our history output. Create ref1f in the unloading part. This should be only set reference 1 every 1 increment and only displacement 3. Ref2f only unloading every 1 sets reference 2 and only displacement 3. Ref3 unloading, ref3f set reference 3 every 1 increment and only displacement 3. So everything is good in the load part. Because we already suppressed this 2 load, we need to create a new load. Load F in the loading F region pressure, and it should be here. And brown is just 1,000, but total force. C is not propagating to unloading step, so we don't need to deactivate that. So unload F. It should be in the unloading region, step, and same region, total force 1,000, and then decreasing. Don't forget the total force and decreasing, otherwise you will get a wrong result. So for this one, we create the modal dynamic analysis of without damping. For modal dynamics, you're not allowed to use parallel computing, but I think you can still use GPA. So submit. So although it's not, you cannot use the parallel computing, it's still way faster than, it should still be way faster than directly time integration. We can wait for a while and see how fast it is. This is getting the mode, different mode. The first step is the preload. See, it's like a 40 increment, 36 increment each time, even without the parallel computing. Now let's go to step. Change the unloading here. Instead of 0 damping, we put a 0.01, which is 1% damping here, and see what happened to that. In your job, everything we can leave it the same, but just name it as NDA with damping. Can submit at the same time. This is already done. We'll wait until this is done. You can see there's some warning here. First is it's about the type. Normally it's no tied to like element, but we can also do node to node, so it doesn't abort your analysis. The other one is like adjustment is too small since we already moved the bin to the correct place. But just in case we can add that one, it doesn't matter. It doesn't affect your analysis. But if you kind of move it a little bit offset, this one can help you to move it back. So I think it's done. So the model analysis is way faster than the directly time integration, especially if you want a long time or very fine time increment. But within a short time, I'll include that later. So let's see the result. So to show the result, we can create 4 different windows here, and then use this tool to show in the correct view. So we are going to add the model. Let me find my result. Okay, so the first one, we are going to add the 100 frames. You can see 100 frames here. Second one, we are going to add the 500 frames. Third one, or you can go to your job and then in your manager, third one, we are going to use see the without. Fourth one, we are going to see the width. So now use this link view and use XZ point to move it to a good view. Shows contour plot for all of that. You can see the displacement U3 here. Now we can see, kind of check like what's happening here. To check whether this is mode 1, mode 2, mode 3, mode 4. This is all your mode shape. And we have in total 30 modes here. So we can move to your unloading frame 1, frame 0. And you can see that I don't have initial condition here. So that means in my step, I forgot to assign the initial condition. True. You need to select this one. Otherwise, your initial condition for the previous step will not convey into this one. So click OK. Now we just rerun this too. This is something different between frequency and time. Frequency, you need to say that whether you want the initial condition or not. But for time, you don't need to specify that. So let's run the width damping first. And go back your step. Since this is already being created, this input file is already been created. You can go to here and change it to 0. And run the without one. That is one way to check whether your model is running correctly or not. Anyway, your first step should be at least very similar, because the first frame for your unloading step should be very similar because they all come from the previous result of static loading, and the static loading should be the same for all 4 models. If you're running 2 models at the same time, your computer may be a little bit laggy. One is already done. Oh, this is already done. So we can select this window and show the result. We can wait until this one is done. Select this window in your job, present the without solution. Okay, now let's go to XZ and then move it to an angle that you like. And then plot the contour plot again, U3, and select the frame independently. Let's go to 0 frame for this one, 0 frame for this one, 0 frame, 0 frame. So this 4 must be very similar, at least very similar. So you can see the value here is, the error is very small. So I would consider this 4 are the same. That means the initial step, the loading step is correct for all 4 graphs. And then we can see a random time. For example, for this one, we select the mid frame, which is 250 frame. For this one, we select the mid frame. Since they only have 100, so we do 50. This one is 250. This one is 250. You can see that for this 2 is kind of similar, while for this one is a little bit slower because we have damping here. Now, finally, we can check the final frame, which is 500 here, 500 here. 500 here. This is 100, and this is 100. 500. So again, you can see that they're already a little bit different now. So you'll see like the difference mainly come from the joint. If you see the lowest bound, they should be kind of similar. Because for this end, it can have some arrows. This is very small. This is a very small number compared to the rest. So if you consider the lowest bound, this is almost the same as this one, almost the same as this one, but this is way smaller than the rest. Now we can see that we can create the XY data for that. From history output, select current frame, and we should have U3 for reference 1, call it as like frame 100 REF1. Plot curve. Select this frame. Oh, sorry. Select this window and create XY data. And then the first one save as call it frames 500 REF1. Let's redo it. So create XY data, history output, this one save as REF frame 500 REF1. Don't plot it in the linked view. Let's do one more here. Okay. You should already have the XY data here. So you should have 500 reference 1 and plot. You can delete all these things. This one can also plot it. And here is, again, XY data, here. XY data, create history output, and this one we have a lot, but we are only selecting the U3 here. So save as, don't apply to link view. So call it NDA without. I will plot here. Well, we just move it here then. You can just plot the XY data. Okay. Oh, link the view. So we create one more over here, and then I think this one of that should be, let's reload everything. I think I mess up in the middle. So this one should be without, this one should be with, and click this one towards XY data manager. We can delete this one first. And then create another one. History output, choose reference 1 here. NDA without. Just don't plot anything. Now we can plot it here. Create this one, click this one, and history output, go down and find this one, save as NDA with, don't show anything, and click plot here. This is a comparison between all the graph. You can see that with 100 frames, is smaller, is coarser than the with 500 frames. For example, some torsional mode, for example, this point is not showing here. And it shows the bending, which is up and down, but it doesn't show the small torque correctly, especially here on this peak and here on this peak. On the other hand, if you use frequency analysis, it's faster and it shows nearly everything compared to your time domain analysis. And if you see the if you see your compared to damping, without damping and with damping, you will see clearly the amplitude is dropping here. This is almost the same amplitude as previously, but here is way smaller than the first amplitude. Sorry about that. So thank you for, this is how you apply the time domain analysis and frequency modal dynamics. So conclusion, modal dynamics is can be faster and more reliable. On the other hand, time domain analysis is easy, is straightforward to understand, but it has, if your time is not fine enough, it can give you some weird behavior. And model dynamics can also have some problem, especially when your mode is a lot, it can have some problem. But that's everything about the model dynamics. Hope that you can learn something from this video, and thanks for listening.